organizers for giving me the chance to speak, and also hi to the online audience. Watch this on YouTube. So I'll talk this. I'll talk about Perverse schobers, and to motivate why you should care about Perverse schobers, I'll begin with applications in representation theory. And so that will be the first part, and the second part, I'll say some words about Perverse schobers. So let's begin with a stratified space. And just think of a manifold, and then stratification means you have nested submanifolds. And then you can define an infinity category, or in an example, in a moment it will just be a poset. So infinity category called the exit path category. Exit paths. And this has the property that when you take constructible sheaves on X, valued in D, this is the same as functors from exit of X into D. So let me say a few words. C means constructible. A constructible sheaf is a sheaf which is locally constant on each stratum. And D is any infinity category. It has to be compactly generated. So this statement is due to Lurie proves this in higher algebra for D spaces, and then Tanaka realized that the proof also works if D is any compactly generated infinity category. And so this allows you to think of, well, sheaves are maybe complicated, but functors maybe not. So that's the advantage of this description. And for us, X will be a graph in the following. So X equal to gamma, the graph. So a graph is just some vertices and edges. And how is that a stratified space? With the strata being either the vertices of the graph and then all the edges, meaning the complements of the vertices in the graph. And let me define in this example of a graph, let me define the exit path category. But I'll just define an example. So consider the following graph. It has some vertices, some edges. Let's do it. So let's also label the vertices. Maybe this is B1, this is B2, this is B3, this is B4, this is B5, this is B1, B2, B3, and B4. Some vertices and some edges. Then what is exit? Exit of gamma. This is equivalent to a poset whose objects are the vertices and the edges. So you have some objects, B1, B2, B3, B4, B5. And then the morphisms, they go from the vertices to the edges. This is why it's called exit paths. The morphisms tell you that you're exiting one stratum and going into another stratum. So this is a very simple poset. It is bipartite. Yes. Okay. And then a main source of graphs are topological surfaces S with non-empty boundary. And in such a case, if you have such a surface, how can you find a graph? Well, you pick a graph, gamma, which lies inside of the surface, which is a homotopy equivalence. So if you have a surface which has boundary, it is always homotopy equivalent to a graph. In any graph, you can thicken it to a surface so that it is the graph then becomes homotopy equivalent to the surface, and this is called the spanning graph. Okay. And we'll look at this in a moment. But so what we'll be studying in the following are then we'll study now functors from exit of gamma into D. And Well, two typical choices of D would be, well, the simplest choices is maybe vector spaces over, say, a field. Or what we're more interested in the following is the infinity category of stable infinity categories. So this we saw on Tuesday already. The objects are stable infinity categories and the morphisms are exact functors. So given such an F.
So maybe you're going to give an example in a second, but if I do like the pair of pants or something, is it easy to think about what the graph is for that?
Well, the pair of pants is just a bouquet of two circles. So one graph would be this graph, but then you may want to insert some additional edges which know about the boundary. So you could, well, oftentimes we want that the graph intersects each boundary component at least once. So you would maybe add 3 external edges, and that could be a choice of graph. But there's, of course, many more choices you could make. So given F, from exit of gamma into cat infinity stable, we define its global sections. As, well, this is denoted by H, gamma F. We think of this as kind of homology of the graph, valued in the sheaf F. This is just the limit of F in cat infinity state. So this is actually all the prerequisites we need about constructible sheaves. I now want to come to examples in representation theory. So the first examples will be Ginsburg algebras. And so we saw them today, 2 talks ago, Ginsburg algebras. And these will be the zero Calabi-Yau version. So this is the zero Calabi-Yau completion. There's a similar story works for all Calabi-Yau dimensions. I should maybe also say deformed and maybe relative, but worry about that when we get there. So, and we'll look at the Ginsburg algebras which come from triangulated surfaces. So let's start with a triangulated surface. So these are any triangles in my triangulation. And then now we want to define the graph in some colors. So we draw into each triangle, we draw arrows, and then we're not defining a graph, we're defining a quiver. So a quiver is a directed graph, and the vertices of the quiver, they are the quiver Q. The vertices of the quiver are the arrows, the edges of the triangulation, and then the arrows you get by you draw into each triangle. You draw a clockwise 3-cycle, and you draw a counterclockwise 3-cycle. So let's call these arrows maybe A, B, C, and then the dual ones we call A star, B star, C star. You also have them here. You draw them into each triangle, and so on. And then you also draw some loops. So here, if we call this edge, call it I, then we draw a loop and we call it Li. And so this quiver Q, this is what I just drew. It is, we consider it as a graded quiver with arrows in degree, we put them all in degree 1. So this is cosmologically in degree 1. And with this quiver, we define the Ginsburg algebra, G, the Ginsburg algebra, as the path algebra of the quiver over a field with some differential. So this is the graded path algebra. And what is the differential? So d of, well, any usual arrow A is just 0. D of A star, this is CB. So whenever you have a triangle and you take a dual arrow, its differential is just the composite of the other 2 arrows in the triangle, going, well, you start with a dual arrow and then you take the non-dual arrows. And each arrow is in degree 1, so the composite of 2 arrows is in degree 2, so this makes sense degree-wise. And then similarly, d of b star would be AC and so on. And then the differential of the loop, we set this to be, well, this is some sum over all arrows, A, and their duals. And then this is a bunch of loops, and you only keep those loops which begin and end at a certain vertex. So you add a vertex, you take all loops, given by arrows and the duals, and then you filter out the loops which begin and end at that vertex, and that you do by composing with the lazy path, or the idempotent. At I. Okay. So this is the Ginsburg algebra. And let me mention that there's 2 different versions of this algebra. So the standard version would be to include, we do not include boundary edges into the quadrant. So this would mean that whenever an edge lies on the boundary of the surface, you don't draw the node and you don't draw the arrows. That would be the usual Ginsburg algebra. And the other version is you include boundary edges, but do not draw loops at boundary. And this is then a relative Ginsburg algebra. And the difference between these 2 versions is this algebra, it doesn't know about the boundary, but it is zero Calabi-Yau. In this algebra, it knows about the boundary, but it is relative zero Calabi-Yau. In the sense in the last talk. So our next goal is to describe this algebra in terms of a constructible sheaf on the surface.
Sorry, when you say graded path algebra, you mean what's the multiplication? Just 3 on the arrows and then with this differential?
Yes, so the path algebra is this is the general construction. If you have a quiver, you can take the path algebra. It's an algebra which is generated by the arrows, and then there's some relations. For instance, well, basically, if there's arrows which are not possible to compose because they begin or end at different vertices, then the relation is that their composite is 0. That's how basically the path algebra is the algebra of paths in the quiver.
Hence the name. Hence the name.
So, but all your generators have degree 1, is that right?
Yes, exactly. This is because it's the zero Calabi-Yau version. The more traditional version is 3 Calabi-Yau, and in that case, some arrows are degree 0, some in degree -1, and some in degree -2. So we need a graph, otherwise we can't think about constructible sheaves on graphs. So what's our graph? We take the dual graph of the triangulation. Gamma is the dual graph. And how do you get the dual graph? Well, you insert a node into each triangle, and then you connect them. That would be the dual graph. And in fact, the datum of a spanning graph, which is trivalent, is equivalent to the datum of a triangulation. Okay. So, define. Now the sheaf f from exit of gamma into cat infinity stable phi. So first of all, we need to say what is f on the vertex of the graph. So let's say v is a vertex. Then we say f of v. This is the derived category of the Ginsburg algebra of a triangle. So you can take the surface just to be a triangle. Then I just define the Ginsburg algebra, and this is this gadget with the above relations and so on. Then if E is an edge, you set f of E. This is the derived category of a polynomial algebra with generator in degree 2. This is also equivalent to the derived category of the path algebra of the one loop quiver with a loop in degree 2. And then, if you have an arrow from a vertex to an edge, what is the functor? F from B to F of B. This is dual to, sorry, not dual, this is the pullback. This is the pullback morphism along the morphism of DG algebras from KT2 into G triangle. And this maps T2 to, well, say we have some chosen vertex I, then this maps it to the differential of Li with this formula above there. So there's no Li here, but I told you about this formula. And this is the morphism. And now the theorem is that if you compute the global sections of the sheaf F, this is the derived category of G. And what is the proof idea? Well, the global sections, this is just the limit of F. And then by abstract nonsense, this is the same as the co-limit. So this is the limit over exit of gamma. Now, we can pass, somehow, we're taking a limit of derived categories, but we can pull the limit inside of the derived categories. And upon doing so, the limit becomes a co-limit. And the diagram, well, is indexed by the opposite coset. This is because here we're taking pullbacks, and the morphisms between the DG algebras go in the opposite direction. So we're taking the co-limit over exit of gamma of the derived categories of something. Sorry, other way around. D goes here. Yeah. D of the co-limit of some diagram in DG algebras. So, and this co-limit is the infinity categorical co-limit. So it's you could compute this by computing it as a homotopy co-limit in some model structure. You choose some covariant replacement and then compute an actual co-limit. And then if you do the computation, if you look at the picture, I'm sure you're convinced that if I take these triangle things and glue them together along loops, then this is this loop, becomes this loop in the co-limit. Then what happens is that you get the derived category of G. Somehow. Seems quite reasonable to that it holds.
So what are the DG categories again that I lost a little bit, the dots?
These DG algebras are G triangle and the polynomial algebra. So I'm gluing the Ginsburg algebra or relative Ginsburg algebra of a surface out of the Ginsburg algebras of triangles and polynomial algebras. The polynomial algebra is also, you can see it as a -1 Calabi-Yau DG algebra of the A1 quiver. As a central mark. So that was example number 1. And now we want to use this example to also describe Brauer. That's a question?
Where's the grading? Is the grading playing any role, or you can just regrade everything?
Yeah, you can basically, same works for any Calabi-Yau dimension. Yeah. So next example are Brauer graph algebras, and I'll try to sketch basically how this computation or this description of Ginsburg algebras can be used to also describe Brauer graph algebras after doing some tricks. And we'll use the following trick. So G triangle, this has a Z modulo 3Z symmetry. What is the symmetry? Well, you just rotate the triangle, and then this algebra is clearly self-equivalent under rotation. That's a question?
Yeah, so you're telling me something that's kind of interesting to me, but probably boring to you, which is that, so are you telling me that if I take a limit of representation categories of some algebras, I can just turn that into a co-limit of the corresponding, as long as my functors are given by some pullback or pushback?
Yeah, because the statement is that passing to derived categories is a functor which turns co-limits into limits. And if you take the pullback, yeah. That's a general abstract nonsense. Okay. So now this has a Z3 symmetry, and let's just define G1 as the homotopy fixed points. So what is this? This can be described very explicitly also as the path algebra of the cover, namely, and with differential. It is the cover with two loops, A and A star, and the differential of A star is A squared. Let me erase the board. So it turns out that these homotopy fixed points, they're the same as the fixed points, at least under some assumptions on the characteristic.
Could I ask about a bit of a mathematical map here? I mean, in this theorem, the goal, the goal is to understand the right-hand side, and the theorem is about it being equivalent to the left-hand side, or what is?
Yes, I mean the right-hand side. So
what is the data? What is the novelty? Do you know what I mean? So
I see. Well,
so you start with a triangulated surface, and out of that you can produce an algebra whose representation, I suppose, is interesting to people.
So let me tell you what are the two new things. So the first new thing is the definition of this relative Ginsburg algebra. This didn't exist before. And this relative Ginsburg algebra exists as the local pieces also. It's not only a global thing, but you can also talk about local relative Ginsburg algebras. And these are then the gluing pieces in this gluing. So this gluing description naturally suggests a generalization of the previous notion of a Ginsburg algebra, which has this gluing property. And the second novelty is, well, these Ginsburg algebras, they existed before. And, well, you just explicitly define them, and this now tells you that their derived category also, well, you can describe it more abstractly in terms of the global sections of a sheaf. And with this, you can now try to do all kinds of things. So you can try to study it using local to global principles. You can try to relate the representation theory of the algebra to the geometry of the surface using the local to global principles. You can also now generalize the if you understand the constructible sheaf well enough, maybe you can say what it means to be a spectral Ginsburg algebra of a triangle, and then you can glue this together and say what's the spectral version of a Ginsburg algebra of a surface. There's a few different things, both concretely, computationally, and maybe abstractly one can try to do with this.
Can you read that formula again?
Which formula?
P of something is something.
So the derived category of the colimit?
No, the little d.
D of A star is A squared.
Oh, it's an A star. Okay.
Yes, that's an A star. Exactly. It's a dual arrow.
Yeah. Okay. So you've got this little quiver drawn above. You've got two arrows.
Yeah, it's a two-loop quiver.
Those are labeled A and A star. Right?
Exactly. Yes. So let me also mention that so the Brauer graph part, this is, well, in the higher Calabi-Yau case, this is joint in progress with Fabian Heiden and Gusio. And I mostly think about the higher Calabi-Yau case, but today I'm talking about the zero Calabi-Yau case, but I think in principle everything is very similar. Okay. Right. Any more questions? Then we have now this new algebra, which is the homotopy fixed points of the Ginsburg algebra of a triangle. And now we look at the following graph. So
sorry, actually, to step back. So you said homotopy fixed points were the same as fixed points in this case?
Yes.
And what were your assumptions on your field again?
I think the characteristic needs to be not 3 for this to be true. I mean, I know it's true if the characteristic is not 3. If the characteristic is 3, I'm not sure if it's true. But I don't know if it's wrong. But it also doesn't play an important role if it's true. So for the Brauer algebra, we saw these on Tuesday in Sasha's talk. So we have a graph, and each graph has a multiplicity. So this is maybe V, this is W, then the multiplicity of V, let's set that to 3. The multiplicity of W is 1, This is also 1, this is also 1. And now, so this is gamma. Let's define a constructible sheaf on gamma. So define f from exit of gamma into cat infinity stable with, so f of the vertex v is the derived category of G1, f of w is the derived category of the Ginsburg algebra of a triangle, and then some more similar definitions, and then the global sections. This is equivalent to the derived category of G tilde, with G tilde being the following algebra. Same gluing computation as before. You get the following result. So here you have the triangle, and here you get some loops. Here you get the two loops A and A star. Then you have another loop L, and then you have one of these arrows by B, and these by B star, for simplicity of notation. And this is some algebra. And now to connect this to the Brauer graph algebra, we pass through the causal dual.
Sorry, how did this algebra come about?
We defined a constructible sheaf on gamma using G1. We attached G1 to the vertex of multiplicity 3. Well, this is just an additional information now. Basically, we're putting here G1, here G of a triangle, and then I'm not telling you what I'm putting here. And then if you compute the global sections, you're just gluing G1 and G triangle, and this is the glued algebra. So
is this a procedure for every graph, or do I have to pick this graph?
No, it works for every graph. Also, it doesn't need to be trivalent, but the formulas become a bit more ugly. So we are focusing now on this one example. So if you pass to the causal dual, so this will be B, in the sense that the finite derived category of G tilde is equivalent to the perfect derived category of B. Then there's a recipe known how to compute the causal dual of these kinds of Ginsburg algebras. And so what you get is that this is the path algebra of the quiver. So let me draw the quiver and then tell you how you come about this heuristically. This is beta, 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 and then this is alpha. So the rule is, under causal duality, each arrow is mapped to another arrow. So A is mapped to alpha, B is mapped to beta. And then if you have a different relation on the differential, so d of A star is equal to A squared, this is mapped to the relation that A star is equal to alpha star is equal to alpha squared. And the relation that d of beta star is equal to beta squared, this is mapped to the relation that beta star is beta squared. So alpha star and beta star do not appear in this quiver because they're just giving you the squares. And then the loop Li, this corresponds to the relation and the causal duality that alpha cubed is the same as beta cubed. So this is the Brauer graph relation.
Beta, there is B.
Yeah, B goes to beta, A goes to alpha.
So on the left-hand side in the equation.
Sorry. So the point is, let me write the slogan. The Brauer graph algebra is causal dual to an equivariant Ginsburg algebra. And this is very, very slogan-esque. We're somehow taking equivariant, fixed points locally and then gluing together. And when we then pass the causal duality, we get the Brauer graph algebra. But you can also restrict this constructible sheaf and just take its value in finite derived category, and then the global sections will be the finite derived category. In this way, the Brauer graph algebra also rises as the global sections of a constructible sheaf. Yeah, and this similar story for all graphs.
Where is equivariant happening here?
Say again?
Where is equivariant covariance happening in this picture?
I'm taking fixed points. So I'm taking basically local fixed points. But one can, this hasn't been done yet, but I think one can do it. Is that, so the Brauer graph algebra, it actually arises as, so you have a surface with these multiplicities, and you take a ramified covering such that the deck transformations, the group acting, the deck transformations, they somehow tell you about these multiplicities. And then what you would want to do is take the Ginzburg algebra of the cover, and then that also has a group acting. And when you pass to the fixed points, you get this algebra G tilde, which is then causal dual to the Brauer graph algebra. And the point is you can not only do this globally, take global fixed points, but you can first compute local fixed points in glue, or first glue and then take global fixed points. This somehow seems to commute, but as I said, this has not been rigorously checked. But that's what the slogan is maybe trying to say. Does that make sense? Yeah, so I already mentioned things about applications, like local to global principles. Another thing one can do with this is if you pass to the singularity category, or the co-singularity category is the dual of that. This is also called the cluster category. You can then try to ask, does the sheaf description also work when you pass to the quotient? And then in some cases that works, some cases it doesn't. And then you can also try to study the singularity category in terms of local to global principles. Things like this you can do.
Will you give an example where it works with the singularity category?
So, well, as for the co-singularity category, I showed that this works for the 3-Calabi-Yau DG algebra, the relative 3-Calabi-Yau DG algebra of a surface. What you then get is the cluster category. You get a cluster category of a surface.
But you still get a decomposition. I mean, the point is here, right? I mean, returning to Paul's question, right? The beauty of these things is that you get a category you don't understand written as some sort of limit of categories which are simpler, right? And
yeah, exactly.
You get the same thing for the...
Yeah, of course. The local pieces will be very simple, and the global thing is, well, maybe more complicated. Yeah. And limits of categories are very easy to understand. You can, well, an object in the limit is just, well, the universal property of the limit tells you what an object in the limit is. It's a compatible family of objects in the things you glue together. So at least studying the objects of these limits, somehow that's quite feasible using using local to global, basically universal property of the limit. Let's now come to the Perverse schober part. So these are some examples which are supposed to get you interested in constructible sheaves or graphs. And now I want to embed this in a more general framework of Perverse schobers. So let again X be stratified space. Then you have a category of Perverse sheaves on X. This is a subcategory of the bounded derived category of sheaves. Constructible sheaves on X, valued in vector spaces. And this is, by the way, this category is equivalent to the category of constructible sheaves on X, valued in the bounded derived category of K. So somehow, derived sheaves are the same as sheaves valued in derived. And so this subcategory is the heart of the Perverse sheaf structure.
Is that K? DBK?
D of K, vect K. Okay, so this is maybe a very abstract definition of what's a Perverse sheaf. But Perverse sheaves are also somewhat complicated objects in general to study. So to have to say anything, we'll now restrict to x as a surface. And then we want the surface now has two kinds of strata, zero-dimensional strata and the complement. So zero-dimensional strata. These are just some points, and we denote them by S singular. We think of them as singular points. Okay. Now with this, we now want to go from sheaves, from perverse sheaves to constructible sheaves on a graph. So first of all, let's go from mess this up. I need to be arranged a bit higher. Perverse sheaves on S. You can go from this to constructible sheaves on the surface, valued in the derived category of K. I mean, this is not the inclusion functor now, this is a different functor. So what does it do? First of all, we choose a graph, gamma, inside S, spanning. And now you map a perverse sheaf F to the sheaf, which maps it open to the derived global sections of the sheaf F on the open U with support on the graph. So this is we use a color. Sections with support on gamma. And then that's the first functor, and the second functor is you just pull back along the inclusion of gamma. And you pass from constructible sheaves on S to constructible sheaves on gamma. And now, what's very special about the category of perverse sheaves is that this functor factorizes. Namely, it factorizes through the subcategory of sheaves on gamma concentrated in a single degree. Depends on your convention, degree 1 or degree -1. And the point is, so you have the remarkable fact is that there exists such a factorization. Remarkable fact, this factors. So where this inclusion is the inclusion of vector spaces inside the derived category, where I put a chain complex in degree 1. And this remarkable fact allows you now to categorify. And why? So if you want to categorify this on this side, well, you just replace vector spaces by stable infinity categories. So replace vect K by cat infinity stable. Note that we don't really know how to replace the derived category of a field by, well, a categorified object, because that would be like studying derived complexes of stable infinity categories. But just vector spaces, they're categorified by stable infinity categories. And maybe one way to decategorify would be taking the k-linear Groton degree. And then on this side, categorification is maybe more unclear, but so the hack, how do you categorify this using this hack? You categorify via image under h gamma. So h gamma is this functor. This is maybe a general recipe, which I want to explain in an example now.
Sure. The one to the dotted area, the one going to the...
Yes. So what's the question, sorry?
If it was h gamma is the one which you viewed as a functor going to the abelian category, right? So this is a functor between two
exactly, it's functor between two abelian categories, yes.
Am I reading this right? So this This dash thing is some purity.
Exactly, that's the name purity.
Homology is like.
Yes. This is similar to the statement that if you have a surface and you compute the first cohomology of the surface relative to enough parts of the components on the boundary, this cohomology will be concentrated in a single degree. And like taking, these sheaves on gamma, they're a bit like local relative cohomology groups. And the fact that they're concentrated in a single degree, this generalizes similar computation for usual homology, but this is now homology with coefficients in a perverse sheaf. So yeah, I think it's quite deep fact that this, or quite surprising fact that this dash arrow exists, and unraveling why that exists computationally is also a bit involved. So it will take some time to do the computation on the board. That's why you have to take faith.
But can you give some idea why we should believe this?
Well, I'll give an example now, and that example hopefully makes it a bit clear what happens in the simplest instance, and then also explain a bit more of this philosophy of categorification, what it means to be dealing with a categorified perverse sheaf. But one thing they certainly induce or give rise to are constructible sheaves on graphs. So somehow, the main idea is that the examples from the first part, they are supposed to arise as these categorified constructible sheaves.
Explain yet what the categorification of the perverse sheaves is.
Well, here you replace vector spaces by stable infinity categories, and then you don't say what's perverse sheaf, categorified, but you say when do I want to consider a constructible sheaf valued in stable infinity categories as a perverse sheaf. So I'll give that in the example. Now, we can arrange these things in place. So S is the complex disk, and S, so just, this is really the simplest space, the simplest manifold. And then the singular, that's just a singular point, 0. So you can draw this like this. This is 0, this is complex numbers, and this is our graph gamma. It's just the graph with one vertex and one edge, which starts at 0 and shoots off to 1. Okay. Now, you have perverse sheaves on C. And you have the functor H gamma to constructible sheaves gamma valued in vector spaces. And there will be something here in the middle, in a moment. And then what's a perverse sheaf explicitly? So perverse sheaves on surfaces, they are, first of all, constructible sheaves. Sorry. Yeah, they're constructible. So this means that there are local systems away from the singularities. So perverse sheaf is a local system in degree 1. This is purely convention. You can also put another degree on C star. So C without 0. And then you have the stalk at 0. And the stalk at 0 is basically where the complication comes from. It not just being a local system. And the stalk at 0, there appears some non-trivial homological algebra. It is a two-term complex. It is a two-term complex. Namely, it this looks like something, some vector space psi, some vector space phi, and then just zeros again. And this vector space is called the vanishing cycles. Sorry, these are the nearby cycles. Nearby cycles. These are called the vanishing cycles. And then, well, the constructive sheaf on gamma, exit of gamma, looks very simple. Just one vertex, one edge, and well, you have a functor out of that into vector spaces.
So do we not have any compatibility between these two ingredients?
Yes, that's the datum, but then there's some properties. Yeah. So that's not having this. Any perverse sheaf is of this kind, but not everything of this kind is a perverse sheaf. Now I'll tell you exactly what it means to be a perverse sheaf. Namely, there's an equivalence between abelian categories between perverse sheaves and the category of diagrams of vector spaces, phi and psi. Here you have two maps. So I think I now change these for this. This is F and this is G, such that if you take GF, GF goes to psi minus the identity on psi, or FG minus the identity on phi. These are invertible linear maps. Invertible. So this is in vector spaces, and so this is a very classical description of this category in terms of this category, both abelian, and somehow the advantage of this perspective is that this is just linear algebra data. It's just two vector spaces, two linear maps with some property, and this is maybe complicated. I mean, they're called perverse for a reason. The definition is complicated. And what is this? This functor from perverse sheaves to, well, sheaves, it maps the perverse sheaf F to, well, the perverse sheaves gives rise to such a diagram. I've only told you what is F. F is the differential of the stock at 0. I've not told you what is G. It's a bit non-trivial to define, but what this map H gamma does is it maps F to the diagram psi goes to G. It maps it to, sorry, psi goes to G goes to psi. So this functor H gamma, it loses information if we have one of the two linear maps, and yeah. Okay. So now I'll finish by telling you what the categorification explicitly means in this example. So this description in terms of linear algebra data has the idea that it's pretty clear how to categorify this. Because for linear algebra, we just replace vector spaces by stable infinity categories, linear maps by exact functors, and then the difference has to be replaced by a cone or a cofiber. So if you categorify, you just have a map from exit of gamma into cat infinity stable, and this is the functor, or some functor from V to n. And here, when you categorify, you use this linear algebra description, and it's still kind of a hack. You say, I want an adjunction, V and N. This is an adjunction. I mean, this is a design choice. If you just have two pairs of linear maps, you could just categorify them by two functors, but it seems natural to require that they are adjoint. And then now you want to say that the identity minus GF is invertible. What is the categorification of that? The cone, let's say cofiber from FG along the co-unit to the identity on V that right? No, on the identity to n. And then you take the fiber from the identity on V to Fg. This is an endofunctor. So the category of endofunctors is again stable, and you take the fiber and the cofiber in this category, and then you have some new functor, such that when you pass to K0, you exactly recover this formula. One moment. And you ask if these are invertible.
You mean GF?
Oh yeah, thanks. GF. Okay. So this is in such an adjunction. Actually has a name before anyone cared about perverse schobers. This is called a spherical adjunction because it generalizes the simultaneous spherical objects, and F is called a spherical functor. And so now, what is the categorified version of the functor H gamma? You just map this adjunction to this functor. And maybe one surprising observation is, above we lost information when passing to constructible sheaves. After categorifying, we do not lose any information. No loss of information. Yeah. So somehow, if we have a constructible sheaf from gamma, relative stable infinity categories, you can say you identify inside of this category the perverse schobers as the subcategory of functors who admit an adjoint such that the adjunction is then spherical. And so my time is, I think, over, so let me mention just two things. So now you can try to maybe unravel these ideas in more general schobers, and then also find a way to pass from such an adjunction, which is maybe local data, to some way to cook up sheaves on graphs. And these ideas exactly then give rise to the constructible sheaves, which appeared in the beginning of the talk. So there's some recipes you can come up with, which turn which input some spherical adjunctions, and which output some constructible sheaves on graphs, and which recover the examples from before. Yes, and another thing, with this kind of reasoning, you can then also try to do everything not linear over field, but linear over any infinity ring spectrum, because many of these adjunctions have a very have a definition which doesn't require any representation theory. It's just an abstract thing. And, so there's definitely a spectral version of the Ginsburg algebra using this general machinery. Okay, so that's all I wanted to say. Thanks for listening.